For quite a while, people have envisioned what life might be like another universes in light of the James Webb Space Telescope, the most shocking telescope in existence. That question can at last be investigated while observing the nearest star system to us, Proxima Centauri, which is just 4 light years away. Researchers have noticed a few extraordinary eccentricities from one of the planets in the system, Proxima B. These eccentricities, called artificial lights, have perplexed the best minds in the field of science. At any rate, what do they do? These lights suggest the presence of intelligent life. Join us as we examine the James Webb Space Telescope's unsettling discovery of city lights that could change everything. The only life that we are currently aware of is on Earth. Since the beginning of human civilization, people have wondered whether there is life elsewhere and in the universe. To answer such an interstellar question, American cosmologists Jill Terrer and Thomas Pearson launched the Search for Extraterrestrial Intelligence (SEI) project in 1984. The primary goal was to gather spaceborne radio transmissions. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the extraordinary Allen Telescope Array in the California lower region mountains. However, for over 30 years, no notable extraterrestrial signals had been found. Following that, the James Webb Space Telescope's successful launch assisted the effort to examine a range of invisible planets orbiting distant stars. As the largest telescope on the planet, drifting about 1 million miles from Earth and equipped with highly sensitive detectors that has the potential to uncover massive radiations. A few decades ago, there were no known planets outside our solar system. However, since been more than 4,000 exoplanets have been discovered orbiting different stars. As outlined by NASA, the universe could contain millions of exoplanets. The earliest indications of something happening far beyond our solar system might be seen in extraterrestrial vegetation. The Galileo spacecraft on its way to Jupiter turned its instruments back toward Earth and saw a clear sign of the presence of plants, recognizing the vegetation red edge of biosignature, a blend of red and infrared light reflected by plants. For example, a planet like Earth covered in wild vegetation should have a marked area of strong signatures easily recognizable. The JWST will measure the V vegetation red edge. A far away Earth-like planets in the habitable zone around stars, which could provide critical indications of something occurring in exoplanets' atmosphere when light crosses a planet star boundary. The JWST may be able to detect it as it enters the planet's atmosphere. The missing frequencies would then be visible through spectroscopy as particles and molecules in the air absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This method could be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres like our own, characterized by a mix of oxygen, nitrogen, and carbon dioxide. By searching for elements that aren't typically present, one might even detect intelligent life. For instance, chlorofluorocarbon CFCs, made for use in refrigeration and cleaning products, would almost certainly be detectable by extraterrestrials studying Earth's atmosphere from a distant location. If the JWST finds CFC in planetary atmospheres, that could indicate the presence of life. However, life on exoplanets likely won't resemble Lithian Earth in any capacity. In some cases, even typical living organisms like extremophile species that can survive in conditions where other living things would die may appear alien. This group of life forms, mostly microorganisms, can survive extreme conditions such as temperatures up to 250 degrees Fahrenheit or strong acid with pH levels below 3, since planets are more likely to support life if they don't have extreme temperatures or acidic conditions. It may be wise to start with those first prime candidates. Could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is a yellow-type star. These stars are rare and usually have shorter lifespans. However, in our galaxy, the chances of finding planets orbiting red dwarf stars, which are more common, cooler, and dimmer than our Sun, are higher. This long lifespan allows for the development of life and evolution to produce complex organisms. About 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST first mission. It orbits a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets situated in the so-called habitable zone could have liquid water on their surfaces despite its smaller and colder mass compared to our Sun. The TRAPPIST-1 star emits light like Earth, which is sufficient for the close orbit of its planets. The most likely opportunity to observe city lights outside our nearby planetary system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Proxima is generally fainter than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable zone, a Goldilocks-like zone where the light intensity is perfect for liquid water. Proxima B orbits Proxima Centauri, but the fact that Proxima B is tidally locked makes it in a potentially airless dead planet since it orbits its red dwarf star just 4.6 million miles away. This close orbit exposes it to strong solar winds that can strip away its atmosphere. However, Proxima B receives enough light for temperatures and liquid water like those on Earth. Due to its proximity to the star, Proxima B is believed to be tidally locked, meaning it always shows the same side to the star, much like the Moon does in relation to Earth. Proxima Centauri is about 18% the mass of the Sun and emits much less light than one might expect for a planet so close to the star. About 5% of the Sun power. This would seem like a desolate wasteland, but liquid water could exist on Proxima B if the planet has an atmosphere to retain heat, since the total energy arriving from the Sun is only 65% of what Earth receives. The planet is not particularly favorable for life. It is likely tidally locked, meaning it always faces the same side toward the star, creating a permanently hot side and a cold, dark side with extreme temperature variations. The planet also receives about 5 times the high-energy radiation that Earth does, including X-rays and ultraviolet light, due to its proximity to Proxima Centauri. Proxima B is also bombarded with high-energy particles during stellar flares unless it has a protective magnetic field like Earth's. Conditions may not suitable for life. Despite these harsh conditions, Proxima B may still be a more habitable world. Unfortunately, models suggest that the atmospheres of tidally locked planets may be prone to the rapid erosion due to the freezing out of volatile gases on the night side. Earth's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, their atmospheres are less likely to escape, since we know nothing about Proxima B's volcanic activity or magnetic field strength. We cannot even speculate whether the planet has an atmosphere. However, since an atmosphere suggests the possibility of life, we are eager to learn if Proxima B has won it. Could have solar pan on the day side to generate power to light and heat the night side, which would otherwise be too cold and dark for habitation. Though discovery of Proxima B has sparked a race to determine if it crosses its star's face is seen from Earth. These transits would allow researchers to determine the planet's size and mass, which would help them assess its density and confirm its rocky composition, providing information on the materials used to form those rocks during a transit. Starlight could reveal the planet's nature by passing through its atmosphere. However, the chance that the orbit will be aligned perfectly so that researchers can observe a transit is only 1.55%. The star's tendency to erupt further complicates matters. Astronomer David Kipping of Columbia University says the star is unstable as stellar heat causes a rocky planet to absorb sunlight and re-it as infrared light. However, rocky planets produce a specific type of infrared radio radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope's design was specifically intended to detect infrared light. Proxima B's infrared signature is crucial for detecting the planet's atmosphere. Additionally, the JWST infrared capabilities, which surpass those of the Hubble Space Telescope, could allow it to detect city lights on the night side of the planet, even if they are as faint as those current used on Earth. The JWST could detect artificial lighting as long as it is confined to a frequency band much smaller than the star's light. Proxima B's day side might be heavily covered with solar panels reflecting steroid as Proxima B orbits its star continuously. The constantly different sides have extreme temperature differences between them. The temperature contrast between day and night depends on whether the planet is made entirely of bare rock or if air and water circulate heat. If there is no atmosphere, Proxima B's day side and night side temperatures will vary more, as the day side will release all the energy it gets from Proxima Centauri as infrared light. The night side would resemble a frozen wasteland if the temperature difference between day and night is less pronounced. We can estimate that future space exploration and the search for life beyond Earth hold enormous potential. The James Webb Space Telescope, JWST, may be the key to finding extraterrestrial life in the universe. As the JWST searches for exoplanets, it will ultimately shed light on the possibility of city lights far beyond the stars. As we continue to explore the cosmos, it's crucial to consider the limitations of our current technology. While the JWST is an incredible advancement, it is still only the beginning of our journey into deep space exploration. There are many challenges ahead in the search for extraterrestrial life. Atmospheric conditions, stellar activity, and the vast distances involved mean that we may not always get clear or definitive signals from distant planets. However, though, potential for discovery remains vast, especially as we develop new technologies and refine our methods for exploring distant worlds. The exploration of Proxima B and other exoplanets continues to push the boundaries of our understanding. Each new discovery, whether it's a planet with signs of water, a potentially habitable atmosphere, or even hints of artificial light, brings us one step closer to answering the profound question of whether life exists beyond Earth. With the capabilities of the James Webb Space Telescope, we may soon be able to see far beyond the confines of our solar system, looking for signs of life and perhaps even civilization in the distant stars. In the coming years, as the JWST continues its mission, we will gain more insight into the atmosphere and composition of planets like Proxima B. The telescope's ability to detect infrared signatures and its unprecedented sensitivity to faint signals could help us uncover not just the presence of water or an atmosphere sphere, but signs of life, whether microbial or intelligent. It's a thrilling time for space exploration, and the potential for new discoveries is almost limitless.